So now returning to the second part of my presentation, to the NZEB conference in DIT on the 29th of May 2015. Having identified that there is an issue with the ACDs and compliance with the mold growth and surface temperature risk factors, we then set about our program this year involved taking a precast concrete house from the 1930s, a terrace of those, and upgrading them to the target NZEB target of 45 kilowatt hours per meter squared per annum, which is the NZEB standard for new build, and we chose to apply it to a retrofit project of this kind. One of the solutions to the project is to prefabricate the insulation elements, to put some extensions on which significantly help to reduce the losses through the floor to the soil block. And in fact, it's possible to, by combination of external insulation, prefabricated extensions front and rear, to retain the existing ground floor in place and achieve the NZEB target for a retrofit. Because it's all prefabricated, it's possible to do this in a matter of a day or two, and achieve full compliance with the building regulations by doing that. One of the things we had to do, because we're not sure whether the FRSI can be relied on, and in fact the geometry of the building with a raised collar required that there was a lot of thermal modelling required on all the junctions. In fact, there were 25 linear thermal bridge models required to assess compliance, both for heat loss and also for surface temperature. So this is what the calculation of the Y factor looked like. 25 linear thermal bridge models, 3 of them in 3 dimensions, which is beyond the scope of the PG Cert course in digital analysis and energy retrofit. So we allowed the students to use the values in the table to Appendix D of the TGDL. And interestingly, the Y factor calculates out at 0.87, which is above the default value, even though all of the junctions are now designed in strict accordance with, well, in fact, are all better than the ACDs and approaching passive house design levels. But yet they exceed the default value. What's interesting is the FRSI has been checked on each case, and in all these cases is the lowest one is 0.81, the surface temperature being 16.2 at worst case, and then going all the way up to 19.5. So we're in very safe territory in the design, and that's an indication of how good the detailing is. The design detailing is that the temperatures are significantly above the threshold 15 degrees C. What is interesting is the cost of doing that. So I've applied a value of €300 to each of those junctions as the buy-in cost for an architect designing this building. Now bear in mind, this is a small 2-story, 2-bedroom house, end of terrace. And there are 25 linear thermal bridges calculations required to be done to check for FRSI compliance. The 300 is generic. I've got no quotes on this, but it basically would allow you to do a baseline analysis of the existing junction to see if it needed to be upgraded, and then maybe 2 iterations of different levels of insulation to see if you had achieved the most cost-effective means of upgrading the junction to meet the minimum FRSI, the minimum surface temperature required. So I don't think the cost of 300 per junction is unreasonable. That's probably what the commercial value of the service is, and certainly when it comes to a 3-dimensional junction calculation, there's significant additional work required for that one. So altogether, the cost of modelling those junctions comes in at €8,400. The minister's share of that in VAT is nearly €2,000. So the overall cost of doing an FRSI check on this two-story, two-bed house is €10,332, which is significantly more than the external wall insulation cost. Now, we need to really look at how we're going to reduce the cost of retrofitting buildings in Ireland. It's probably more cost effective if we actually take the ACDs and really look at them in detail. We do the modelling, we apply the correct surface temperature resistances, and we redesign the details so that they are suitable for use in accordance with both the backstop and the more common NZEB target U values of 0.15 or even better. So we need to look at a much wider range of U values for the flanking elements, and we need to redesign the details so that they are compliant even with the U values down as low as 0.08 for certainly for ceilings, and 0.1 probably for walls. The cost of doing all of that is about €100,000 on a national basis. We do it right, do it once, and get all our ACs up to scratch. It would take about 3 months and employ 5 researchers to do that. The alternative is really the nightmare scenario, which is that we pay $10,332 for each home to check that it complies with the building regulations. And we've got 1.3 million homes to upgrade to the NZEB standard by 2050. The total cost of that is €13.4 billion. I think it's clear to say that between those figures there is one which is cost optimal, and actually we are required by the directives to ensure that we only undertake work that is cost optimal. So there's a very clear choice to be made by government in finding the means of achieving that cost optimality. And finally, I'd just like to say that DIT, the Dublin School of Architecture and Building, looks forward to working with government and the construction industry to resolve all the technical issues necessary to achieve the NZEB retrofit required under the Energy Performance of Building Directive and the Energy Efficiency Directive by 2050. We need to do this safely, cost effectively and speedily, and working together we're confident that we can achieve all of those targets. There are no insurmountable technical difficulties. We just need to make sure that our regulations are up to standard in achieving the NZEB standard. And that's the second part of my talk. Thank you very much.